So for another example of a proof by contrapositive, let's consider the following proposition. So for this proposition right here, we have integers m and n, and the claim is if m times n is even, then m is even or n is even right here. So you can see again, we have an if-then kind of statement. So this is our P and that is our Q. And looking at this, if I tried to use a direct proof technique, this would be rather difficult to do, because if I assumed mn is even, then it'd be 2 times some other number, but how does that relate to just m or just n? So a direct proof right here would be a little bit difficult. So instead, let's go ahead and try an argument by contrapositive. So my proof is going to declare that I'm going to argue contrapositively. So to argue contrapositively, I have to first off figure out what is the contrapositive of this statement that I'm trying to show right here. So I have to do a little bit of scratch work on the side. So my scratch work So my original statement is mn being even implies either m is even or n is even. Okay, so I need to take the contrapositive of this statement right here, because in my proof of contrapositive, I have to consider the contrapositive of this statement. So the contrapositive of this thing, this is going to show us why we were talking so much about those different rules of logic, like De Morgan's law, because I'm going to have to take the contrapositive of this statement right here. So to do that, I am going to negate this conclusion right here. So that means that I'm going to get m odd. So I'm using De Morgan's law right here. So that means I'm going to flip the or to an and. N, instead of being even, is going to be odd. That's going to imply not this statement right here. And not this statement is mn odd. So I've used here in my scratch work a couple of different rules of logical operators, like De Morgan's law and how to take a contrapositive. So now that I've done this, I know for this contrapositive statement right here, what I have to assume is this. I have to assume that m is odd and n is odd. And what I want to show, is that m times n is odd. So just over here, I'm going to say want to show. So that little WTS is an abbreviation for want to show m times n is odd. So let's see here, what do we have to work with? I assumed that m is odd and n is odd. So let's go back to the definition and write down what it means for these things to be odd. So by definition of being odd, m is odd means there exists some other integer such that m is 2 times it plus 1. Here I'm using k1. And n is odd means there exists some other integer, here I'm using k2, such that n equals 2k plus 1. And what I want to show is that m times n is odd. And so the cool thing about this is it immediately makes us think, well, if what I'm trying to show is m times n is odd, and I have an expression for m and I have an expression for n, let's go ahead and just multiply them together and see what falls out. So I'm going to consider m times n. So I'm going to substitute this expression in for m. And I'm going to substitute this expression in for n. Right here. And I'm going to go ahead and expand this thing out. So if I expand this thing out, I get this nice big expression right here. Well, don't lose track of what we're trying to show. We're trying to show that m times n is odd. M times n, we are almost there because all I need to do is factor out a 2. Just like that. So, I have shown that m times n equals 2 times some other integer, this nice complicated expression right here, plus 1. Therefore, there exists some number t, and I've actually given it to you right here, it's odd, and I can go ahead and conclude my argument right here. So this is a perfect prototypical example of a proof by contrapositive because it required a little bit of scratch work on the side to apply our rules of logic, and then simply going back to the definition of what it means to be even or odd, I was able to then immediately, after a bit of algebra and simplification, show that this is going to apply, that my m times n is odd right here.